Deakin University is one of Australia's largest universities, located in the state of Victoria in the country's southeast. A highly regarded educational institution, Deakin has more than 32,000 students. In recent times, the university has also been developing a reputation for world-class, cutting-edge research, especially in the area of advanced materials for both the auto and aerospace industries. Deakin maintains close links with government, leading corporations and the broader community to ensure that the research is relevant, innovative and outcomes-based. One of Deakin's most enduring links is with the Ford Motor Company.
I'm Bernard Rolfe from Deakin University, and I'm the team coordinator for the Model T project for Deakin University. We'd like to welcome you to our submission for Model T for the 21st century, which we've codenamed T². Deakin University's partnership with Ford Australia goes back to 1988, when the company was instrumental in the introduction of a new generation of industry-responsive undergraduate engineering degree programs. Based on this partnership success, in 1997, Deakin University and Ford Australia developed a collaborative research partnership called STAMP. STAMP was about providing cutting-edge leading research of manufacturing into the Ford factory plant. Our story begins with the invitation in February 2008 to participate in the challenge, which was followed soon after by the design brief. We first established a team which included an overall steering committee and a design team with technical stream leaders. In addition, we invited participation from within the university and across many faculties, including architecture and building, business and law, science and technology, and the Centre for Material and Fibre Innovation. Additionally, the project received excellent advice, feedback and support from Ford Australia. Our steering committee then set about determining where our non-traditional consumers were situated. In Australia's Asia-Pacific region, there are more than half the world's population. Australia is highly engaged in the region and is well regarded for its technical excellence. And indeed, our Prime Minister is fluent in Chinese language. Deakin University is also well established in India. Professor Peter Hodgson is well regarded within the region, and he has initiated the development of a large applied research centre to be situated in southern India. The growth in non-traditional consumers is coming from the metropolises in India and China. For example, Shanghai is around 25 million people and growing. This is our target market. As a part of the design process, we conducted a brainstorming session with participants from all over the Asia-Pacific region. This highlighted a few important key features for our vehicle. These included city driving, flexibility in use, agility, space saving, easy to park. This session also indicated that if we wanted to dominate a decade of the 21st century, like the Model T did, then our concept needed to be easily upgradable for both software and hardware.
Deakin's design objectives were to provide $20,000 worth of performance for just $7,000. Integrate high-quality passenger protection. Build a robust, lightweight vehicle. Create a step change in the manufacturing and assembly of the vehicle. Minimise environmental impact. And offer consumer appeal for a wide and diverse market.
We then focused on the design. This started by reviewing the ingenuity of the original Model T. One of our emeritus professors, John Duncan, helped us. He'd written a book on the engineering of the original Model T design called Any Colour So Long As It's Black. The original Model T made use of existing combustion engine technologies, but the innovation that Henry Ford brought was a very clever but simple, robust design that was easy to manufacture. Simplicity in design appeared to be the key. Henry Ford also used the latest steel technology from Europe to introduce high-strength steels to the USA. Now back to reality. The vital change that we saw that had to be made from current vehicles is the move away from the combustion engine. The choice became one of electric engines, fuel cells, hybrid technology, or something else. At Deakin, we chose something else. We found a design of compressed air rotary motors in the Melbourne region, the Pietro motor from Engine Air.
The Pietro air motor is based on a rotary piston. It uses a simple cylindrical rotary piston that rolls with minimal friction inside the cylindrical stator. Motor speed and torque are simply controlled by throttling the amount or pressure of air into the motor. The pt1 motor gives instant torque at 0 RPM and can be precisely controlled to give soft start and acceleration control. The small size, lightweight nature and compactness aids in the integration of all components in the car.
The emissions from the rotary air motor are simply cold air. Why did we decide to use compressed air? When we thought about electric engines, batteries are the largest drawback. Long-life batteries are expensive to produce and require a large amount of energy, high carbon footprint, to produce. Batteries are also difficult to dispose of at the end of their life, and compressed air motors are much lighter and simple to produce. The compressed air motors were also compact in design so that they could be used as wheel hub motors and could supply sufficient power to drive the vehicle. The torque characteristics provide high starting torque at very low revolutions of the shaft. The other important consideration was that the air motor only consumes air when the car is moving, so there is no fuel wastage while the vehicle is stationary at the traffic lights or in a traffic jam. Also, the direct drive of the wheels from the hub motors meant that we could eliminate the need for a gearbox. This also eliminates the driveline and steering rack and pinion systems, which contributes to a further reduction in the carbon footprint. To create an even more agile car, we've decided to use only 3 wheels. 3-wheelers in Western countries are a rare sight. However, 3-wheel rickshaws in India and China are a common vehicle on their roads. We've designed the 3-wheel vehicle so that it maintains stability. That is, it has been designed so that the wheels will slip before the car actually tips. To achieve the 200-kilometre range, we've had to include a natural gas burner in the powertrain. However, for a lesser range of 80 kilometres, only the compressed air is required. Compressed air centralises the carbon emissions to the powering of the fuel compressors, which can be powered by renewable energies as shown in our submission.
Using the 2 direct drive hub motors allows for a simple differential steering system. Controlling the speed of each wheel hub motor independently allows the vehicle to steer. This, combined with a trailing single rear wheel, allows the Model T Square to turn on the spot, making it easy to navigate into tight parking spaces. To ensure the vehicle is stable at higher speeds, the rear wheel is passively damped by a rotary steering damper, similar to the one found on the handlebars of motorcycles.
The use of compact wheel hub motors means that our vehicle has to be incredibly lightweight. To achieve this, we have stepped away from the traditional body structures of current cars. We also wanted to find cost-competitive manufacturing processes that we could also use for production. Our research on advanced materials and manufacturing processes within Deakin led us to investigate roll forming of ultra-high strength steels. We can roll form ultra-high strength steels which have low formability, thereby adding strength and reducing cost. Our vehicle structure will be a hybrid of a roll-formed ultra-high strength steel floor and a subframe, with a polymer A and C pillar roof rail made of thick epoxy reinforced glass fibre. Doors lined with a stainless steel mesh laminate with fantastic impact properties, and a back thermoset panel.
Because of its inherent strength, the fuel tank has been integrated into the vehicle as the key structural member. The air tank's fibre-reinforced plastic structure also provides the excellent stiffness needed for it to be the backbone of the vehicle. The air tank is manufactured through a filament winding process with the mounting rings attached to the tank via a single co-curing process. The air tank is attached to the vehicle via high-strength extruded aluminium tubes.
The exterior panels are reinforced polymer parts made by the novel resin transfer moulding process and are recyclable. Resin transfer moulding can be combined with a quick-step process which is being researched at Deakin, and this will increase the cycle times. The advantages include reduced costs on multiple press lines and complex stamping tooling, as well as increased flexibility in exterior vehicle shape. This innovative structure enables us to have flexibility in the engine